Dear listeners, welcome to the second part of the online international workshop, Diffusion and Interdisciplinary Investigations. I would like to present to your attention Professor Alexander Garbany. He will finish his course of lecture, Data-Driven Artificial Intelligence, Problems and Ideas. Please, Professor, you are welcome. Professor Garbany, please turn on your microphone.
Okay, sorry. Fine now?
Yeah.
Presentation is available?
We don't see your presentation, unfortunately.
I don't see my presentation. Strange. I see it. Let's start again. Apologize for technical. Oh, somebody is here instead. Okay?
Yes, now everything
is fine. Okay, so hello, my friends. I'm happy to meet you again. Today I will finalize my very brief and very non-technical introductory lecture course, mini course, Data-Driven AI. And lecture 3, Logically Transparent Neural Networks. So, as I told in my first lecture, there is one pebble in our shoe. And one addition. First pebble was, the main was errors of AI, and unexpected and very often unusual, unhuman errors. The second is decisions are not transparent. It cannot be explained logically. This is, of course, we did many people, and even in the 90s, we developed software that produced logically transparent neural networks by pruning and combination pruning and learning. And the lecture will be about the explainability problem. I should say that this is, first of all, before all specific content, I should say that this is a long discussion. Discussion is explainability needed or not? Because, for example, I know very famous researchers in neural networks, they say that large neural networks are unreadable and they cannot be explained as exactly as our brain don't explain us how it works. Our brain decisions are not explainable. We post factum, we invent some logic, but if you make a step, you have no explanation why do you make this step. If a football player runs and plays this direction, he cannot explain logically. In boxing, if you start to explain logically, you will fail. Therefore, so this one direction is logical explainability is not needed in many cases. Another part says, oh, these your damned black box neural networks, they're absolutely unclear. We cannot work with them. We cannot trust them because we don't understand them. This discussion perhaps is infinite, but I should say that there are two very, very clearly articulated positions. Now let's go. Explaining programs. Glass box. This metaphor of glass box or transparent box instead of black box. The decision should be explainable to a human. Well, this is idea of all explainable AI program. XI, explain this abbreviation XI. But another requirement is that this glass box should be understandable, but should be not worse. Is it always possible? I don't know. I'm not sure. But this is a mission of this program. We should extract explicit knowledge from black box models. We should verify the system is consistent with our ethical and social and legal values. And then DAPRA. DAPRA is a famous body, Defense Advanced Research Project Agency. It's military agency, so not this supports, but it supports many other research programs. In some sense, in Russian, we say double direction, double usage problem, and so on. The DAPRA initiated XI program to focus efforts on United States and international researchers there. I advise you to look on this web page of the program. So how they explain DAPRA? What is XI? I like this explanation, very clear. So today the training data, machine neural networks learns, then learn machine functions and gives decision or recommendation. And then the user does not understand why does machine do this? Why not something else? When this machine will succeed, when this machine will fail, how can I trust? And so on. This is a user questions. Again, I should say that this is very simple loop because the modern world, the loop of action is almost immediate, and many actions are not just recommendation, direct action of the machine, learned machine, and user just observes these direct actions and tries to understand what to do. This is not just recommendation. And XI should work through explanation interface, and user is expected to be happy with understanding why and why not, that he can expect to have proper expectation, and he can analyze errors. This is a goal. The below line is the goal of the XI program. Then let's go to slightly, because AI is absolutely huge area, let's just focus on neural networks today. Not the benefits of NN, universality. Universality, absolutely. So it can do everything, maybe something good, something not so good, but everything. Something well, something not well. Universality as an approximator of any automata, of any machine, and so on. Proven in 1990. And Dropbox, black box solution. Not everybody is happy. Infobesity program. It's a special word, infobesity. That's information obesity. If, of course, neural networks algorithm is absolutely clear. Just take the structure, look on these thousands or millions of connections. This is algorithm, but it's too big. We cannot read it. No, normal people cannot read it. No normal also. Nobody can read millions of connections. If there is a structure, then it will be overloaded. Too rich neural networks have tendencies to overfitting. Too poor cannot learn. And we have many requests to implement neural networks of small devices. And there is some questions. How many inputs do we need? How many connections do we need? How many connections do we need to solve problem? And the last item here, and solutions are not unique. This is a special of course, we know this since 1996, but at the end of 90s, it was invented a special metaphoric term, Rashomon effect. Rashomon is famous novel of Akutagawa Ryunosuke, and the famous Kurosawa movie, Rashomon Gates, where several truths exist. Several people tell, and what is the truth if people don't know? Everybody tells something and we don't know what is the absolute truth. And even, does it exist? Or it does not exist. So NN pruning can resolve these problems partially. Pruning idea is very simple. If you start from pruning, just cut what is not necessary, as a gardener prunes a tree. Some sociology. Here are two plots. Neural networks total, as Google statistics. Publications, maximum of neural networks publications was in 2012. Now neural networks publications go down. It's a huge number. 200,000 per year, don't worry. 200,000 links in Google Scholar per year, it's huge. But that drops down. And the publications with pruning, not so many, but this is still exponential growth. Pruning attracts more and more attention now. And this is interesting, the fraction of pruning papers through neural networks papers. This is an explosion. Now we observe an explosion in the fraction of pruning papers. Why? Because people start to pay much more attention to the logical explanation of neural networks skills. Problems where pruning is applicable. Feature selection, removal input neurons, or just input links. A search of appropriate architecture, removing of neurons in shallow and neural networks and filters and convolutional neural networks. It's not too very useful idea. The deep neural network samples are too deep. Reduction of precision of synaptic weights. Now we work with weights, weights are real, sometimes even with high precision. For implementation in hardware, we need less precision. The best idea is just bit precision, 0, 1. Of course, bit is not so usual possibility. Maybe we need too many synapses for this binary synapses. But the byte precision is more or less appropriate for many problems. And we don't need 10 to power something, we just byte. Cheap and fast implementation. Replacement of accumulation function with a simple function. Uniform network simplification for knowledge extraction. Usage, and then of truncated convolutional neural networks as future generator. There is a CNN is not United States TV. CNN is convolutional network here. Sensitivity indicators. How we can decide that this element should be pruned? Of course, a gardener looks on a tree, looks on the branches. This branch is not so good, can cut. There are several. There's hierarchy of sensitivity criteria. Zero order. This element has rather small signal going through it. No, small signals, small weights. Small weights with small signals can be deleted. First order. First order are a bit more sophisticated. We look on the goal function, objective function, the goal, and look how significant will be the change of the objective function of the goal if we delete this element or change this element. It is gradient based. And the second order, we can use the Taylor series, you can apply second approximation. The reason for this is when we work near the minimum, all gradients are expected to be small, and at the minimum we should look on the second derivative, Hessian. But you can understand that Hessian requires square of dimension. It's not, so some approximation of Hessian I use it, not Hessian itself. And since 1990, it was more or less clear that the first order indicators are efficient, one, first, and second, don't require much resource because they utilize the training information. We calculate gradient in training. Just go along the trajectory and integrate the sensitivity indicators. Like now it has a special name like integral by along trajectories. So how we calculate sensitivity? Let L be the go target, go objective function. We can calculate derivatives GL on dW, weights, derivatives by inputs, and derivatives by outputs. Because if output is not important, we can kill the neuron. Then we can calculate gradients. Then we can calculate gradient sensitivity indicators as integrals along trajectories. Now, first of all, we can use like Lagrange approximation, so first order approximation. Then we can select the maximum, because this L, if you have the multi-criterion objective function, vector objective function, then we can calculate the maximum for the criteria weighted, and this is maximum for Lj, the maximum among the criterion for multi-criterion function, and then go and average along the trajectory of training. We have trajectory of training, and then we calculate, and that is the average. Then we go, we can look how it works. We can somehow, this illustration, we go along the trajectory of, red is trajectory of learning, and the average along the trajectory. You should pay attention to that. If the one-dimensional optimization in learning is rather good, then the next gradient will be orthogonal to the previous gradient. And therefore, we need to average along many steps. This, I should say that this illustration is a bit too optimistic, because learning is not a minimization of the objective function along the descent in ellipsoid cap. No, this rather sophisticated, rather complex optimization landscape. This is just to understand how it works. That algorithm is simple. Take many parameters, save M, how many will we cut, save current neural networks, calculate, select elements, modify, retrain. If after retraining the total loss function is not so good, then break and return. And go in loops until everything works. If you fail, then decrease the number of deleting elements to delete and return, and so it's very simple loop. Very simple. Okay. Which elements can be selected? It is very interesting question. First, the smallest scale, synapses and features. But sometimes neurons and filters can be evaluated as a whole, not just signal by signal. So we should care about all input weights of neurons. If the output of this neuron is not important, just cut. And then we should like to uniformly simplify neurons. So, for example, to have, if a neuron has 100 inputs, it's very difficult to read. Maybe should somehow reduce, for each neuron, reduce the number of inputs, uniform simplification. That is somehow a strategy for pruning. Then knowledge instruction. No, it's an absolute idea. All synaptic weights are 1 or -1. All activation functions are step functions. And then we should look on this neural network and say, oh, everything is simple. Of course. And because I don't like to discuss many, there's nothing to discuss at that level. Then if we go inside the algorithm, there are some hidden difficulties, but not for today. Let's go to an example. I like this example. The data for this example were collected 20 years ago, even more, by Lichtman and Keyles-Baroque. And this is a simple toy example for many classification devices. This is United States presidential elections. I should say that once this system failed as a Bush-Gore competition, the system insisted that this should be Gore, but the Supreme Court of the United States decided that Bush won. So this is, I don't discuss politics. So there are 12 inputs you can read. 12 inputs, and we say you can create a 2-3 layer neural network to predict who will be the president using the history. And of course, we can select some president for test set, some president as a learning set, training set, and then learn. Everything is as usual. And then we apply pruning. And then we have very clear Rashomon effect. Here we have 1, 2, 3, 6, 8 semi-empirical, 8 transparent networks. Some of them are ugly because the static criterion was not applied. Some of them are very nice, like the second or the third. 3 neurons, 5 or 6 inputs. Signals go from below to up. Synapses are marked plus and minus, like +1 and -1. There's no value, just sign. Let's analyze one example. This is semi-empirical theory. The first algorithm, we have 2 syndromes, 1 and 2. So first and most important attribute was there was a serious contest for the nomination of the president party candidate. Yes or no? And if it is yes, it's very. Then the second is 6. Was the election year time of recession and depression? And the third is, does the president initiate a major changes in national policy? This is novator. So this is this negative. So this 8th attribute is the president is novator, but with minus it means he is not novator. This sum gives us the first syndrome in adequate governance. Sorry. The second syndrome is political instability, third-party activity plus serious contest for the nomination again. You see, attribute goes, attribute with contest and nomination goes in both syndrome, and there was more major social unrest. So there are two syndromes, plus and plus. If these are positive, the opposite party wins. So if one, so this is, there are two inputs, two syndromes to the final neurons. If both are positive, if as operation O is 1 is positive, because 0, 1, the result is, then opposition party win. For winning for opposition party, it is sufficient to have one of these syndromes. Of course, we can analyze the second algorithm. Again, we see the high importance of the concurrency in the president party. Let us omit this and let's go ahead. This is, I think that this is clear. We cut everything what we can, and we have a rather simple theory of change of power. And for example, let me go a step back. If we look here, we see there's a syndrome symptom number 4, it's called the first level symptoms. Symptom number 4 is crucially important. Therefore, the opposition party should pay much attention for the organization support of strong competition and in the presidential party. This is the logic of the political fighting. And then it should be investment, could be investment into third-party activity, and could be investment in social unrest. If somebody invested in these three, if two of them work, the president will fail. Okay. Multiple solutions. Sometimes I met much why do we need multiple solutions? We need unique solution. The truth is unique. But what should we use? The answer is, unfortunately, the truth, perhaps in reality, especially in so soft reality like social, politics, medicine, the truth is not, could be not unique. And the conflict with, there are different probable, there could be different but probable diagnoses, there could be different but probable solutions. And at least if you have non-uniqueness, we can plan the further data collection and sometimes the further operation to make the situation, to shift the situation in the direction we need. So the technical take-home message. Of course, first, pruning is useful. And sociological pruning is a hot topic in neural networks analysis. And the third, sociological, explain artificial intelligence is a very hot topic. Then technical take-home. First-order sensitivity indicators can be used to evaluate sensitivity on synaptic weights, neurons, inputs, outputs, and intermediate signals. The second, all proposed pruning procedures can be implemented in the unified framework. There is a special framework, very simple in this logic, how to implement everything. Combination of proposed pruning algorithms can be used to solve any listed pruning problem. And the logically transparent network can be read. Yes, but it is omnipotent or not is a question. So then the final accord, when the explainability of AI is needed. So, when? Experience. And here I will argue with this Psi program. Unfortunately, there is a law of human nature. Users are lazy. Users prefer, from our experience, the one-button solutions and use this option rarely. We provide this system. It works for 20 years. But when users use this option to create logically transparent neural network, it is necessary to analyze errors. When people find errors, they would be happy to understand which signal, which decision, which element is responsible for that error. And that, my claim is that the very optimistic point of view that users will look, understand. First, it's too difficult. Users will not, most of users will not look and understand, but they will look and understand when the errors occur or when the possibility of error is very high. A smell of error appears. So, explain AI is needed when AI make mistakes. To decompose the erroneous decision into elementary steps, to understand which step is wrong, to distribute the responsibility for this mistake, to correct the erroneous step for the future, is simply to simplify. Credibility is simplicity. But does truth resist simplicity? I don't know. Several fresh references, just fresh reference, because now there is no canonical text about XI. Therefore, if you like to look a bit more, you should go to the XI program page, very optimistic because they advertise their program, but very professional point of view. And here are several fresh publications for medical domain, for users, for human AI systems, or a combination of human AI systems, and with some literature review. And this is Mirke's review of my co-author, maybe 100 references and some explanation of our algorithm. Thank you. Questions, and I ask you, ask the questions for the whole course.
Thank you very much, Professor Garbani. It was a very interesting lecture, and of course, we have some questions for you. So the first question is, what are the main differences between neural network and convolutional neural network in practical tasks and at all?
With neural network and I missed one word.
Convolutional neural network.
Convolutional neural networks is a special sort of neural networks. It means that of course, what's neural network? The main element of neural network, maybe go back. Oh, this is adaptive summator. Adaptive summator historically was proposed by Woodrow in 1961, and then for first Adeline analog, first backpropagation, one element backpropagation rule, and then that this linear functional can have a form of convolution. Convolution is a particular case of a linear functional. That's all. When this is needed, when we work with large fields and we would like to work with shift invariant properties, then we work with convolutions. It is useful for when it's needed, for image, for analysis. For language analysis, we move along the text. For genome analysis, we move along genome. Then convolutions is a very reasonable operation. It's a particular case of adaptive summator. And then convolutional neural networks are organized in many, many layers with special intermediate nonlinear selection of winners, this nonlinear selection. And this is large convolutional network. But essentially is that. More questions, please.
Okay, thank you. The next question is the pruning algorithm you presented general, or it may have some modifications?
Oh, of course, it has many, not only may, it's a good question, but it has many modifications, but most modifications, so first of all, how to select the sensitivity indicators, there's some, let's go to sensitivity, oh, this is the sensitivity indicators. Of course, evaluation of error. What sensitivity indicator? It's just evaluation of error after we change the element. Of course, the objective function is vector, so this is multi-criterion, but if you can forget about J, just objective function. Then you can select. We can use some second quasi-Newtonian approximation, second order approximation. Then you can use absolutely cheap, just no signal cut, no signal cut, no signal cut. This is zero order. It also works, not as good. It requires it deletes a bit, sometimes deletes too much fat, and or leaves too much fat because it's not so flexible. Or you can say we take very already well-trained neural networks. This is second order criteria. Then you have this is a huge area of creativity for creation new indicator. Then the logic it could be very flexible. What this is? Select elements. You can select so many elements. You can decide, for example, there are algorithms for coloring. We color neural network. So therefore we should say red and blue. We should say that red color can be pruned, that blue does not take. Blue is some sort of skeleton we should keep, and so on. Then there are other elements where you can add some social criteria. For example, the discussion about ethical, how to include ethical criteria, that the pruned neural networks logic should satisfy ethical criteria with this race equivalence and so on. There are many versions, but the basis is more or less the same. Okay.
Thank you very much, Professor Garban. And we have one more question. It was the question from the first lecture you gave. So the question is, do you think, is it possible to create artificial general intelligence?
Whoa. It's very difficult. Of course, first, how to understand the word possible? If you go to the space of absolutely formal possibilities, the answer is yes. Of course, yes. If you go the possibilities, the sense of observable future, I say not now and not in the nearest future. And then in the final, if you speak about the possibility as a result of development of technique, the development of necessity, technical possibility, the question is very often connected to the question of the technical necessity. because very difficult problems, even if you in abstract sense can solve them, will not be solved because they are not needed. I don't think that this problem is technically needed. Therefore, yes, but first, yes, but no and no. In absolute sense, yes. In the sense of nearest future, no. In the sense of technical necessity, at least in the horizon of my vision, no.
Okay, thank you very much. And
excuse me, may I just? I couldn't
Professor
pose a question.
Jäger, okay, you're welcome.
Can I?
Professor Jäger.
I wanted to ask the following. We have the chance to have good connections to John Hopcroft, who is one of the leading people in computer science, in deep learning also, and he's advising the government of China. And he makes the following statement, and and I would like to know your opinion. He was asked the question, is artificial intelligence real? He answered, no, at the current state, artificial intelligence is a pattern recognition in high dimensional space. AI programs do not extract the essence of an object and understanding its function or other important aspects. Another revolution in 40 years may accomplish this.
Okay. Okay, so.
Let me just add something else. I think what you pointed out for me is very important. Artificial intelligence needs features for the data. And they do not all come from the data itself. It needs an interpretation of the features.
Yes. Okay, thank you very much. Tomorrow I will give a lecture exactly about your first question. I completely agree. My question, what I will discuss, is artificial intelligence and intelligence. Is it an intellect? Is in Russian, I apologize, in Russian, является ли искусственный интеллект интеллектом? Because in Russia, intelligence and intellectual is the same. The question is no, and there is a very simple test, much simpler than Turing test I will give you. Take the Rautine-Wechsler IQ test. There are several subtests, but sometimes some of them are very simple, like look on the sequence of numbers, close and reproduce. Of course, computer could do it much better. The second is, for example, this anagram. You have a word with mixed letters, and what is the word? Computer is much better than a human if he has
clearly
a dictionary. But, for example, this explain metaphor without metaphors. Computer fail, because this level of language is unavailable for computer now. Then, please take some picture, for example, an elephant or bird cut in the pieces and combine. Is on the edge of ability. But is the most important is, please take a boy or girl, a school boy, give them the test they haven't seen before with these tasks, and they will solve somehow. Computer is extremely far from this situation that he or it still it takes a test and never seen before, it starts to do. Is absolutely far from that. Therefore, a structure, machine is much powerful in its world.
That's clear, absolutely.
And also, and then I should add one notion, because it's a lecture. I ask not answer not to you, just to the whole audience. There is a special notion introduced by Marvin Minsky, a notion of micro world of artificial intelligence. Each device which we call artificial intelligence has its own micro world with own micro ontology it works in. And then this micro world is it should be much more powerful than the human, because we don't need it. But in general world, we have no such AI. So this is a question. So it's not intelligent, it's not intellect.
But explaining refers very often to this world. For instance, if you use deep learning in medicine, in medical data, I can tell you what happens because we do it. And our people from computer science present us answers if the feature one is indicator for sepsis or not.
Yes.
But they did it. And then I looked at the result and told them number 1 is wrong, number 8 is wrong, number 15 is wrong. And they asked why. Why is this the case? Why can you tell? Because I can combine it with understanding of processes, of relations between the objects.
Yes.
And this is missing. Therefore, it has to come together.
Yes. So this is another problem, also well articulated, the problem of extraction of deep knowledge from data. Deep, not in the sense of the number of convolutional layers, but deep in the sense Einstein had almost no experimental data of deviation of gravitation from Newtonian, but he created general relativity just because deep thinking and deep knowledge. Okay, thank you. Perhaps we run out of time.
Okay, thank you.
So
thank you very much. Thank you,
for
Professor Ilya Yeager, for your question and discussion. Professor Gabon, many thanks to your very interesting course of lecture. It was very pleasure to us. So, dear listeners, we'll have a break until 4 p.m. Moscow times.
Hi, Claude. We met before. Okay. In Newton. Okay.
At least in web seminar you can smoke. That's one good thing.
Let's continue our workshop, and our next lecturer is Professor Bardos from the University with the lecture Vlasov equation from derivation to quasi-linear approximation. Please don't hesitate asking your question during the lecture.
Okay, so I guess it's my time to start. I move on full screen, okay? Here I am on full screen. I am going back to the quasi-linear approximation and at variance with the last talk, the talk from yesterday, where I used randomness. I want to approach the same problem through a classical spectral theory, which leaves the way to go to Landau damping and arrive to a classical short-time asymptotic to the, with some open question after that. So, once again, the contribution is to the relation between the Vlasov equation and the quasi-linear approximation. I have put the equation depending on epsilon, and I didn't scale it, but here is the Vlasov equation. The E now is really done, depends on the Poisson relation and to the Poisson equation. And then just below, there is an equation for the, which I call the quasi-linear, for the density of particle, the density integrated over the domain. The domain is the torus, or if it's a compact domain, it will be over the compact domain. So it's a balance of all the profile with respect to velocity. And the best I can do, but I won't comment on that with no randomness, is to justify this equation through a correction term which will be of the higher order than the diffusion. Okay, so far so good. So the use is go back to the classic quasi-linear approximation, and that's it's something which is very classic in basic plasma physics. I use the book of Kral and Trivial-Peace, which is already of the 1970, and I want to introduce a more, let's say, modern mathematical derivation based on functional analysis, and it leads naturally to a comparison with the Landau damping. So that means that the structure of the talk of this afternoon is a spectral property of the linearized Vlasov equation near a stationary profile. This will lead me to the introduction of what is called the Penrose instability condition and the asymptotic expansion of the solution. Now, there was an idea of Villani and Moore to precise the Penrose stability condition. And that was of the main tool they used to get a nice proof of the Landau damping. And I will make some comment on that, and also this will also allow me to return to the first talk or the second talk where I mentioned the rescaled solution and compare what the Landau damping say, what the rescaled solution would say. After that, there is a simple justification of the quasi-linear equation, which means the term of the order of epsilon 3. And since it's the last talk, I may flash some general conclusion at the end. Okay, so far so good. So first, there is a stationary profile, which is a function which depends just on v. Put it in the Vlasov equation, it doesn't move. It's a stationary solution. So since it's a stationary solution, I can look at linearized version. Linearized version of the previous will come with the unknown will be h, and you have the derivative with respect to x and t of h here disappear. Here you have the electric field, which depends on h, and then it's again the gradient with respect to v of g. So this is called the quasi-linearized system because it's linear. So far so good. Since it's linear, you can deal with that either by the Laplace transform or by the Dunford calculus, which is almost the same thing. Dunford calculus, as in the book of Cato, will be slightly more modern. But anyway, if you make a Laplace transform of this equation, since it's linear, you make Laplace and Fourier. Fourier will change h into h of k. Laplace will change it as a function of lambda. Laplace may appear lambda here. Fourier may appear this quantity. And this equation in Laplace transform turns out to be what is written here, and with the fact that that as soon as we have done the Fourier transform, the Fourier coefficient of the by the Poisson equation, the Fourier coefficient of the electric field is ak over the modulus of k square, multiplied by the Fourier coefficient of the density. So the Laplace transform appears here. Turns out to be very simple. You move here, there, and then you have a simple equation. And if you want to solve it, you would rather be able to invert this quantity which is in bracket. That will be what the Laplace transform will do for you. Okay. So if you go back to some classical functional analysis, you know that the advection operator, V grad x, is just the generator of a unitary group on the torus, and that's just its spectra. It's very simple. It's just the imaginary axe, which is written in red. Now, this term is a perturbation of the spectra. Since it's a perturbation of the spectra, it's a bounded perturbation, but even more so thanks to the Poisson equation, which computes the electric field in terms of h, it's a compact perturbation. So by classic theory of semigroup, if you take any positive line here, and you look at what's happened in the spectra there will be just eigenvalue of finite multiplicity in this region. There will, whatever you have a delta here, in this region you have just eigenvalue of finite multiplicity. And if you go back to this equation in terms of the density, you will return here. You just have to invert this quantity. And to invert this quantity means that this quantity has not to be zero. So you identify the eigenvalue from frequency lambda m as real number A and R at such that there exists a frequency so that this quantity is equal to 0. Having put the detail between the lambda m, which is the Fourier Laplace term, and the Fourier coefficient, this turns out to be exactly what was found by or referred as a Penrose equation. So you characterize the eigenvalue of this number as having a companion frequency, so that this quantity is not 0. And you are interested for the instability at the region when they are on the right-hand side, and that will be the Penrose equation. Now, if what you find out is that whenever you have lambda km, you can look at the corresponding evolution equation, which means you divide by you use the previous equation. It's lambda minus ak dot v, the gradient of v, the frequency at the time 0, exponential e lambda t. There is no I here, there is an I here, and this means that this quantity here with no I will be exponentially increasing. So the Penrose equation gives the mode which are unstable solution of the linearized equation. Moreover, there is an important property, no I here, is that you have the solution here, the electric field, which means they are both related by the equation lambda plus akv, h lambda of t and x, and a of tx plus gradient of v equals 0, which is the equation 5. Before going on, it may be interesting to compare this equation 5 with what was the object of my talk yesterday, because this equation says that this unstable solution and the electric field, they move with the same frequency. The evolution of the H is driven by the evolution of the electric field and vice versa. In some sense, as I wrote, they are slaved one to the other, and this is the opposite case of the case which was the object of my talk yesterday, where in fact I had an electric field which was completely independent, and it's the fact that it was independent because it was a stochastic random field which made the convergence to the diffusion to the nonlinear diffusion equation. Here it will be the opposite regime where we will also get a diffusion equation, but through the slaving between the two quantities. Now, if you have simple root of this equation, you can express, as you assume that you have simple root, you can express any solution as a sum of that modulo a small exponential term. These ones are unstable. They are growing as the exponential lambda t, and the delta, which is here, is nothing else than the delta, which is here. So I just take into account the eigenvalue with real part greater than delta. So far, so good. Okay. Now, what is I want to compare with the Landau damping. The Landau damping, as observed by Landau, refers to a situation where the electric field goes to 0 when the time goes to infinity. And of course, that corresponds to situations where there are no solution of the Penrose equation. Otherwise, solution of the Penrose equation will increase. So I'm looking at a regime where there will be no solution of the Penrose equation. Now, the first natural idea will be to try to extend the resolvent of the positive part of the semigroup into the shaded region. And this is related to a certain number of scattering methods, which are standard in scattering theory. It goes back in the 60s of the last century. I quote Cato, Lax, and Phillips. And but then you have to cross the image. If you want to extend this thing, you have to find a way of crossing the imaginary axis. Crossing the imaginary axis introduce some kind of monster of functional analysis. You can do that just using an interpretation of the extension in the sense of dual of analytic function. Now, it turns out, and that was introduced by Sebastiano Silva, it appears in a book of Case, which was a standard book of nuclear transport equation. I have a former student, Degon, who wrote it in a more modern way. But what happens here is that rather you just restrict slightly the Penrose condition, and resting it, as it was done by Villani and Moore, you can focus on the density. And if you focus on the density of the fluid, of the particle, which is the integration of the unknown with respect to the velocity space, you have a much easier way to extend, and you have arrived to a computation which is almost user-friendly, which is the one I may talk about in the next slide. Okay, so the idea is to start with this formula, which is just an integration with respect to S, which you do, and it works because you may take the Fourier transform of the profile. The profile is the stationary profile is a function of V. Then the Fourier transform, you make the Fourier transform, changing this variable V into a variable eta. So this is the Fourier transform with respect to the velocity of the profile G of P. So then by integration by part, you get this equation, which is an integration from infinity. Here the lambda is correct, G, J, K of Ks. And what is the, so these are the two things. And what is the form that Villani Moore proposed? Instead, just to say that this quantity is not zero in the real part of lambda positive, they say that it is bounded below in absolute value by a number k0, and they show also that this is a reasonable condition, slightly more general, but not so much. For instance, in dimension more than 3, it will be true for at least 3. It will be true for any profile positive that will be invariant under rotation. Otherwise, in 1D, it means that if you have a bump in the profile, the bump is not too big. When you have done that, you want to do estimate, and you save the game, because estimate will use this is exponential, maybe exponentially growing. When lambda becomes negative, you will save the game because the GKS being analytic, its Fourier transform, and that is the Palais-Wiener theorem in simplest form, say that the Fourier transform will decay. As a consequence, one has the following, we take the density, you take the Laplace transform of the density, becomes a little more complicated, but it's a thing that you can compute reasonably. It involves the Fourier transform of the initial data. which means you have taken the Fourier component, and you have taken the Laplace transform, Fourier transform of this guy. Now, if you have these two quantities which are analytic, you have an estimate here, and you have also the same type of estimate on the initial data, which means exponential decreasing k, exponential decreasing modulus of ks. Then the two functions which appears in this expression can be extended analytically in for the real part of lambda negative. They can be extended due to the balance with the frequency, can be extended in a region where this frequency appears, which is this is greater than that, which means at the end of the day you get a nice expression of the Laplace transform of the expression in terms of 1 over the modulus of k squared plus k squared. And this will give it, so that in some sense will give a decay in terms of the initial data. We can be improved even, you don't need this exponential, you can make it a little more and go to space slightly less regular. This is, let's say, for the Gevrey space, but you don't need this point for the detail. Okay, so you have a very nice expression for the linear problem. Since it's so nice, you can try to look at the nonlinear theorem by perturbation. So in fact, this is this presentation is well done in a very user-friendly way of Grenier, Nguyen, and Rodiansky. I wrote the reference on arXiv. It's this year, and what they do, they start from this nice relation on density. Of course, the problem is non-linear, but as it has been observed already by Villani and Moore, there are, of course, some interacting mode that you have to control. It's called the echo. But after that, from this simple linearized estimate, you will move to the nonlinear, and you will obtain the version that we want of the Landau damping, which is that if you have an initial data, which is of this form G of V, plus a small perturbation, you assume that G of V is analytic, H of 0 to sake of simplicity analytic also, but that can be improved. And then if the G of V satisfy the stability estimate of Villani and Moore, which is the improved Penrose, then the electric field goes exponentially fast to 0. So that's the Landau damping in a slightly more modern way than Villani and Moore, but it's on the same line. Okay, now what I talk in the second talk, I was considered the problem of finite time with a rescaled equation, and it's just implied that by just the ergodicity of the free flow, this quantity converge weakly to something which is independent of x. So if you are interested in the Vlasov equation, you need the potential. The potential you have to invert the Laplacian against a function which is independent to x with a hypothesis of neutrality that gives you 0. Because so that means that in a weak sense, as soon as I put the epsilon, I get a weak convergence. Now I wrote a theorem that can be deduced from the previous slide, is that if I take a perturbation, bounded perturbation of the initial state, I can just adapt the theorem of Grenier, Thoran, and Rodiansky and prove that in this case you don't have only a weak convergence, but you have a strong convergence, which means that in some sense, and if you have a strong convergence, the diffusion of the limit of the scale, as observed in the last talk, the limit of the rescale diffusion equation, rescale transport equation, will be a diffusion with zero coefficient. Okay, but anyway, I just explained why we did call this analysis the baby Landau damping, because we get very easily, in a nutshell, the weak convergence to zero. However, the strong convergence gives you a situation where at the limit, the electric field will converge strongly to zero, and that the diffusion coefficient of the diffusion equation limit will be zero. And the proof is in nutshell, because you can just deduce it from the previous result by a rescaling, introducing instead of f epsilon xv, introducing f epsilon t over epsilon square. That will move an epsilon here, and moving an epsilon here, you don't need to put an epsilon in this point to apply the machinery of the Thoran, Grenier, and Rodiansky. So let's give this point. Now, that says that basically, if you have no eigenvalue, if in the regime of the Landau damping for large time, you are in the regime of the Villani-Moore estimate, and you rescale the equation, you won't see any interesting nonlinear diffusion. Now, to see, I will move to the more detailed analysis for short time, illustrating what I wrote here, which is that the presence of eigenmode, which are the mode which increase, there appears explicitly in a short time asymptotic solution, but that will lead to the quasi-linear approximation near an unstable profile. Unstable is because you have eigenmode. Unstable because you have eigenmode. And that's what I want to explain. And this, in fact, was what you found in the old textbook of plasma physics, and this is what I want to go through, just explaining what are the mathematical difficulty, what goes on also with the interpretation of the physics. Okay, if I can. So the first very natural idea is to split the function, for any epsilon positive, as the sum of the profile and the small perturbation. And the profile, you assume that it is integrated over, this is the profile, and then you assume that it's constant with respect to x, and so you assume that if you integrate this one with respect to x, you assume that this is equal to 0. So you split the solution into something which just depends on v, and something where you have taken the average with respect to v from here, and something which is of 0 average with v. Then you decouple the Vlasov equation in two pieces. One will be epsilon squared, the gradient of v, of the integral over the torus of E of h dx, and you put in the other equation the remainder. So the remainder will be dt of h plus v grad x plus eh grad v, and you put on the right-hand side what you have. Here, if I would have written the Vlasov equation, there would have been a dt of g, but the dt of g, you put it here. From there, and you use the fact that this is of the order epsilon, the h is of the order epsilon here, so you simplify by epsilon, and there is, instead of an epsilon square, there is just an epsilon. So this two equations, which I call 20, turns out to be equivalent to the Vlasov equation with a small perturbation. So far, so good. Now, I want to show that their solution, for which I will have the quasi-linear approximation that I have in mind. To do that, I don't want to be in the Penrose or Villani condition, so I assume that there is at time 0 lambda such that I have a solution of this equation. And that gives me an initial data, which I will call f epsilon 0 of x and v. It's the zero profile at 0 plus the small perturbation x epsilon x and v, which I write in more detail, explains 0 of v plus epsilon e k 1 of v g0 of v over lambda plus ek. Here I wrote it in the space in terms of the corresponding coefficient Fourier of the electric field. As you see here, it's still the case where the H is slaved with this quantity. Okay, now this is the solution in lambda of an algebraic equation, of an analytic equation. It has a solution for time equals 0. The true solution of the Vlasov equation, one can show that it is an analytic solution. This has been worked by several people. I have the name of Ben Ashur in mind. And since you know the solution, this is an equation with an analytic dependence on time, I assume that lambda is at time 0 is a simple root. By standard expansion, you can, standard continuation, you can prove the existence of an analytic function, lambda of t, which will correspond to an analytic k, such that this equation remains valid. So, if I do that, I introduce the approximation. An approximation will be no more a solution, which is ek gradient of v g of t of v plus lambda of t, and I fix the k. I just move the lambda of t exponential ekx. So this will be not an exact solution, but I want to turn the crank and show to you how it brings in a second order correction. Okay, now, this, if all that will be of constant coefficient, that will be, as in the beginning, solution of the linearized equation. Well, so I move it. Now, if since it's not a solution of since thing moved by time, if I move this quantity into the linearized equation with an h near g which depends on time, that will not be 0, but the difference involve just the derivative with respect of time, the derivative with respect of time of g, and the derivative of the respect of time of the lambda of t. Now, the lambda of t depends on g. G is analytic, and I have written the equation in this form. So since h is a perturbation of order 1, the time dt of g oscillates at the velocity epsilon square. So in some sense, it's a slow variable with respect to the h. So there is an epsilon square. So since all the remainder in this formula will just come from the derivative with respect to t, you get here an O of epsilon square. Then you look at the difference between the real solution and this ansatz h tilde. Put it in the machinery, And here you add an epsilon. On the right-hand side, you have quantity which are the order of epsilon square, plus something which is slightly bigger, which is the order of epsilon square. So all that together will give dt of epsilon square, the gradient. You move it on the top, that will you just use this thing, move it in the equation for G, which was the equation for G, which I will recall, which is here there was an epsilon square. When you have used this ansatz, you got just 1 degree more, you get in epsilon 3. Now, what is the progress? The progress, you have moved the epsilon 2 to an epsilon 3, and also you have replaced the h by something which was built by the Dunford calculus, by the epsilon, instead of h, it's h tilde. This is exactly something that you can compute. And I'll go on the computation. You know that I go back first to the computation of h tilde. You see h tilde is completely explicit in terms of g, in terms of lambda of t. So you can put that in the term which is here. And if you do that, you use the nice relation between the grid drift and the time, and you obtain an equation which is of the form, for G, you have an equation of T with 1 degree more of smallness, which is epsilon 2 replaced by epsilon 3, a gradient of G, and here you have a very nice coefficient which makes appear the velocity, the real part of the lambda is the velocity at which this increases. But since the diffusion equation, it has a damping effect, and the quantity just below is positive, because it's the sum of the real part of lambda is positive. So that gives you a solution with 1 initial data like that. Now, of course, you can combine it not only with 1 eigenvalue, but you can combine it with all the eigenvalue and asymptotic solution involving all the eigenvalue that did correspond to this quantity. And you have the delta here. So this way you have obtained the best you can do for short time of the asymptotic behavior of almost any solution in terms of its projection on the unstable mode. You have an epsilon square, here you have an epsilon, and you have the term that you have neglected, which gives me arbitrary small, provide that delta goes to 0. And so that gives you a description of what happened for short time. And you see in some sense that at variance with the Landau damping, you have a diffusion coefficient for the nonlinear diffusion, which people could call the quasi-linear approximation, as in my talk yesterday, with a quantity here that increases with time. But since it increases with time, it stabilizes the G and brings it to 0. So it's a good description of how the thing would stabilize for a short time. Okay, so that's the story I wanted to tell you. I just want once more to argue that at least for tokamak, for a certain number of practical questions, looking at the total space density where you integrate over the domain is a physical important domain, and it will work as long as the free flow exhibits some ergodic property. You know, if, for instance, the torus, the free flow is ergodic. If you have a domain bounded and you look at the free flow with specular reflection, it will be ergodic. Now I want to compare once more what I did yesterday and what I talked about you today. Yesterday it was based on a randomness hypothesis. It was the independence lemma, which makes the operator ET and the density function, let's say at the time S, independent as soon as S minus T is greater than epsilon square. And that was for large time with something which is completely random. The other approach which I wrote today is completely different. It's for short time and where things are related by the density and the field. They are completely correlated. It's the opposite because they are linked or slaved by the Penrose relation. Now, I told you at the beginning that I wanted a diffusion that will not be zero. These two scenarios are compatible with the fact that you have a diffusion zero. At the limit, simply for the first one, you had the ergodicity and you had the decorrelation. For the present one is because I work situation where you have an epsilon square, which make this go to zero, and I look at the epsilon at the point of higher order. Okay, now the other thing is that looking at the expansion of solution in terms of a small parameter, in fact, that was a game which was also played in the beginning of the time where people look at the way to connect Navier-Stokes, the Boltzmann equation with the Navier-Stokes before the thing were done more systematically, as it has been recently done. And this is the way it's done from Boltzmann to Navier-Stokes in the paper of Chapman and Skog or Ellis and Pinsky. There is in this way of doing also an analyticity hypothesis, because if you want to push the thing to higher order in epsilon, you can do that. But in the meantime, you get end with problems which are only well posed in the analytical setting. Okay? Now, I just want to finish with this comment. The proof which I gave right now, it's inspired by the book of Kral and Trivialpiece. There is more spectral theory. I just prove, in some sense, that things are moved from epsilon squared to epsilon 3. There is something which has skipped in this proof, which should be fixed, is that epsilon 2, epsilon 3, it's modulo some derivative with respect to V, which appears in the computation, and I put it under the rug, but it can be fixed if you look at a formula that will involve the control of derivation, which is what you do when you use a Nash-Moser type problem. And the last comment maybe is that we have two different scenarios. The two different scenarios, they apply in plasma physics. The big open problem will be to find a way to put a bridge between how you describe things where they just increase for short time and how you describe it for very large time when the thing due to the large time also becomes as driven by a stochastic potential. So that's the end of my story. I thank you very much.
Thank you so much for your lecture. It was very interesting. For now, there are no questions. We hope they can appear during the discussion section.
Yeah, I can turn the...
Thank you so much.
Okay. Okay. question. I can get the participant. Equal, but apparently I don't have any question. I don't hear anything. Maybe I have no question.
There are no questions now, but maybe they appear in discussion section.
Okay.
But now there are no questions.
Okay, I will also be there for the discussion section. Thank you.
It would be nice. Thank you. Dear listeners, now we have a short break till 5 p.m.
Okay.
Okay. Okay. Do you see my presentation?
Not now. We have 2 minutes.
I
Start.
I would like to... Я хочу показать мою презентацию, я поделиться экраном, потом иду на рабочий стол. И там на рабочем столе должно появиться мое... Вот я сейчас включаю.
Dear Professor Greens, please switch on your microphone. We don't hear you. Oh, okay, it's okay.
Good evening.
Okay.
I hear. And I would like to, but I don't see my presentation at this moment. You see?
Нет, сейчас не видим.
Да что ж ты будешь делать? Сейчас, секундочку. Вот тут поделиться экраном. Вот рабочий стол. Вот я иду на рабочий стол и сейчас выкладываю презентацию. Сейчас должно получиться. Ну-ка, получилось?
Да,
все.
Отлично, мы видим.
Okay. Good evening, comrades. I am very glad to continue my mini course. And today I will speak about chaotic dynamics. And I would like to explain one of the way of appearing of chaotic dynamics. Chaotic dynamics appeared in 16th of century, last century, and after opened structurally stable dynamical system with chaotic dynamics, with infinite number of periodic points. When we consider first my lectures, we consider discrete dynamical system with finite number periodic points. But thanks to Smale and Anosov, it was opened that there exists structurally stable dynamical system with infinite number periodic points. So we have chaotic dynamics. And I try to explain how they appear on two-dimensional surfaces. Okay. Goal of the lecture. The goal is to present interrelation between properties of geodesic lamination on close orientable surface of negative Euler characteristic and existence of chaotic dynamical system on them. I recall some definition from Lobachevsky geometry on Euclidean geometry of Lobachevsky plane. Hyperbolic plane Lobachevsky plane is Poincaré disk model. It means that we consider on complex plane disk, and it will be a hyperbolic plane, and set circle S infinity. It is called absolute. The straight line in this geometric are arcs of Euclidean circles that are orthogonal to S infinity. Endpoints of geodesics, ideal endpoints belong to S infinity. You see by red color some straight line. You see point A, and where exist two parallel in different direction, which don't intersect A, but they have the common ideal points. Excuse me. This and this. And if we consider any geodesics, any straight line, they are not intersects in this domain. So it's the sense of Lobachevsky geometry in this model in Poincaré disk. Okay. A hyperbolic isometry. What does mean hyperbolic isometry? Hyperbolic isometry is pre-surface orientation delta and has two fixed points belonging to S infinity. One fixed point is sinc, you see, and another point is source. So if we consider restriction of hyperbolic asymmetry at the circle S infinity, it is very simple Morse-Smale diffeomorphism with sinc gamma plus and source gamma minus. Okay. For hyperbolic isometry, there is a unique geodesics L gamma that is invariant, and its endpoints coincide with fixed points of S infinity. So it's very important that there is invariant geodesic for H isometry. And by the great theorem Poincaré and Courbet asserts that given any close orientable surface M2 of negative Euler characteristic, there is finitely generated properly discontinuous group gamma consisting of hyperbolic isometries different from identity such that our surface is space orbit, is factor space. Okay, so in this picture is drawn fundamental domain of this discrete group, and its polygon such that if we glue this side to this side, this side to this side, this side to this side, and this side to this side, we get surface which is pretzel. Okay, so it's surface of genus 2. The hyperbolic plane delta is universal covering for the surface M2 with natural projection pi. So it's very known concepts for specialists in topology and geometry. Okay. We introduce the concept of rational and irrational poise on absolute with my teacher and colleague Samuel Ranson. Every non-identity element gamma has two fixed points, gamma plus and gamma minus, as we know, that belong to circle at infinity as infinity. And gamma plus is a sin, gamma minus is source. We call each fixed point of gamma a rational point. The set of rational points of all elements from gamma different from one density is countable and everywhere dense in circle at infinity as infinity. The points of complement to the set are gamma on S infinity we call irrational points. Let's try to remember the concept of irrational poles because it's very important concept for me. Okay. Projection with natural projection with axis is closed geodesic on M. It may be simple geodesic or not simple geodesic. However, it's closed geodesic on M. Okay, it's also very important. So for us, very important person for surfaces was Jacob Nielsen, Danish mathematician, known for his work on homeomorphism on surfaces. His work was very important for us. And he not was connected with dynamic. However, his results was very useful for understanding dynamics on surfaces, in particular with chaotic dynamics, okay? Fundamental Nielsen result. Let's don't hurry and try to understand this result. Let F and 2B2 be homeomorphism. A homeomorphism bar F on Lobachevsky plane with such commutative diagram is called lift of F. Let F and 2 be an orientation preserving homeomorphism. And let F bar is lift of F to the universal covering. When F bar extends to unique homeomorphism, delta closure, so it's delta union with absolute, which we denote by F bar again, and set F restriction to circle at infinity, F bar star. Next results, the K results in Nielsen theory. Let F2, F1 be orientation preserving homeomorphism. If F1 homotopy to F2, when given any lift F bar 1, there is a lift F bar 2 of F2, such that they coincide on absolute. Vice versa, if F1 and F2 have lifts respectively such that they coincide on absolute, then F1 and F2 homotopy. I would like to explain that any homeomorphism has very, very many lifting. However, if we have for F1 such some lift F bar 1, for F2 lift F bar 2, and if these lifts coincide on absolute, then these homeomorphisms are homotopic. So we have very many continuum different homotopic homeomorphisms, but all these homomorphisms may be continue on absolute unique way, okay, in some sense, that I explained. Let F and 2 by 2 be orientation preserving homeomorphism, and F bar be a lift of F to the universal covering. Well, we can consider map. We take element gamma of group gamma and consider homeomorphism F bar minus 1 gamma F bar. So it's easy to check that it will be also some element of group gamma, capital gamma. So we have some isomorphism from with gamma to gamma. We take gamma and get new element F bar minus 1 gamma, F bar gamma. Okay, it's also very important concept in Nielsen theory. Induce automorphism of group gamma. It depends on some sense from lift of our diffeomorphism or maybe homeomorphism, but it's possible to understand what happened. Let F1 and F2 be lifts of F when there is gamma 1, 2, such that F bar 2 is equal gamma 1, 2 superposition with F1. So it means that F bar 2 star is equal gamma 1 to minus 1, F bar 1 gamma and gamma 1 2. So it means that automorphism F2 star connected with F1 by means of inner automorphism, A gamma 1 2. Okay, so we have very many lifts and we have very many automorphism for given homeomorphism, but all these automorphism have simple connection one to each another using by some inner automorphism. Okay. Definition. Very important definition. Its definition will be connected with chaotic dynamics, the existence of chaotic dynamics. An automorphism tau gamma to gamma is called hyperbolic, provided for every zeta belonging to gamma and n belonging and natural n. Iteration of gamma is not equal to gamma up to inner automorphism. Never, never, never not equal. If we deleted zeta, it means that tau and gamma not equal gamma. But we admit sometime, but we more stronger condition that for any zeta is not equal. According to Nielsen, so what geometrical sense of this condition, of this definition that automorphism tau is hyperbolic? Let me listen to me. According to Nielsen, it's very important result, which is not true for higher dimension. For any automorphism tau, there is a homeomorphism F M2 to M2, such that for some lifts, F star automorphism fundamental group is equal tau for some lift on the map F. And automorphism tau is hyperbolic if and only if for any n and any closed curve L, which is not homotopic to 0 on M2, the curves L and F and L are not homotopic. So what does mean hyperbolic automorphism? It means that any homomorphism which induces this automorphism has very, very interesting property. If we take any non-homotopic curve, after all iteration, we don't get homotopic curve which is homotopic. For if we have geodesic non-homotopic to 0, so all images of this geodesic not will be homotopic to origin geodesic. So it's very, very important result for hyperbolic automorphism. So at this moment, I already would like to say some important claim, some important statement. If we have some homeomorphism of surface negative curvature such that it induces hyperbolic automorphism of a group gamma, I claim that this homeomorphism has in non-wandering set infinite number periodic points, period of which go to infinity. very beautiful results. So we nothing more about homeomorphism. We only know that this homeomorphism induces hyperbolic automorphism, which means that any geodesic not maps to homotopic to origin. In this case, this homeomorphism has infinite number periodic points. I would like to emphasize that Nielsen did not know this result, unfortunately, because he, at that moment in his life, he had no example of homeomorphism. He knew that this homeomorphism exists, but he did not know properties of such homeomorphism. And me and Aronson and independently Thurston constructed such examples in class of for automorphism, which is hyperbolic. So now I explain how such homeomorphism and such diffeomorphism appear in hyperbolic dynamics, which is possessed by chaotic properties. Okay? Homomorphism of absolute induced by automorphism. Let tau be automorphism of group gamma. For gamma belongs gamma different from identity. We said tau star gamma plus is tau gamma plus, tau star gamma minus, tau gamma minus. At the picture, it means that this point go to this point go to this point. And so, according to Nielsen, the map tau star extends uniquely to the homomorphism of the circle, which we denote by tau star again. Moreover, if f m2 homomorphism such that f star bar is equal tau for some lift f bar of the map, when f star is equal tau star. So continuation of homomorphism f star bar coincides with tau star. It's very important property, and it's very important Nielsen result. Okay. So now it's very important that the property of hyperbolic automorphism it's possible to see on circle at infinity. Let tau be hyperbolic automorphism of the group gamma. I recall that it's such automorphism that any geodesic don't go to homotopic geodesic. Where an even number n and n element gamma such that the homeomorphism tau n star gamma of the absolute induced by the automorphism a gamma tau n has positive even number mu fixed points. So all the fixed points are irrational, half of them being sinks and the other half source. It's very important and surprised results. We used certainly Nielsen result. It's theorem by Aronson Greenis, however, we use Nielsen theory to prove this very surprised result. If we consider tau, we don't know about his behavior on absolute, but we claim that if we consider some power of results and multiply by some inner automorphism, we get homeomorphism of absolute with finite number fixed points, in some sense more small homeomorphism of absolute. Sink and source, nothing more. Okay. Now what we do? Consider the point S1, U1, S1, U1 neighborhoods, because such that of homeomorphism tau star, such that on this only 4 points on this arc of absolute. There may be else points, but we take neighbors points. U2, S2, U1, S1. Okay. and denote by geodesic GU, GS. I recall that point U2, US2, U1, S1 are irrational points of absolute. They are not fixed points for some element of group gamma. That is very important. Okay. Very surprise fact, if we project these points to this geodesic to surface, we can study properties of these geodesics. Theorem. The set omega U, closure GU, omega S. So what does mean? We take GU is projection of capital GU is projected GU small, and we consider closure of this geodesic. So we claim that it's a minimal geodesic lamination, which is non-wire dense in M2 and consists of non-trivially recurrent geodesic. It means each geodesic is dense in omega U, omega S. So it's such lamination is locally is product counter set and some interval. The number of connected components M2 minus omega U, M2 minus omega S is finite. Each of them du ds is homomorphic to the disk and accessible from the interior boundary of du ds consists of finite number of boundary geodesics. So if we consider lamination and complement of lamination, it will be some triangle or another polygon, and this boundary from inside is union of finite number geodesic. Okay. Theorem. We can say about asymptotic direction of its geodesics on Lobachevsky plane. Endpoints of average geodesics in omega U are irrational. So this lamination consists of continuum curves. And on Lobachevsky plane, any curve go to absolute on two direction, and limits of any geodesic only 2 points for one direction and another direction. And points of every geodesics are irrational. Each connected component of this set, delta minus omega bar and omega s, so it's preimage of this lamination on Lobachevsky plane, is some polygon with finite number sides. And there is a picture. So, for example, triangle, rectangle, we don't know what is in polygon, but in this picture is triangle for omega s and for omega u. Okay, they have transversal intersection. So we have for any hyperbolic automorphism of group gamma, we can construct two transversal geodesic lamination. If two geodesic omega omegas have a common endpoint on the absolute, when they belong to the boundary of some polygon PU-PS. It means that each geodesic of lamination omega U has asymptotic direction into asymptotic behavior on two directions, such that almost all geodesics has different asymptotic direction. Only two direction can have common point on absolute, but in this case they are boundary of disk on absolute. Boundary from this admissible from interior. Okay, but another geodesics have different asymptotic direction. Okay, so it's key moment for theorem of classification about I tell you. So now I will say more quickly, and maybe it's necessary to explain, but however, unfortunately I have no time, but I give definition. Let a man be closed smooth manifolds, and F be diffeomorphism. Yesterday we say about hyperbolic periodic points. Now it's generalization of concept of hyperbolic point. Non-wandering set is hyperbolic if there is continuous DF invariant splitting of tangent bundle in sum of stable and unstable summand bundle, such that the following estimation holds. So we have in two-dimensional case, we have two directions, and any vector is invariant on these directions, and for stable bundle, if we have such estimation with vector after iteration, norms go to 0, and for W, which belongs to another subtle bundle, its norms go to 0 under negative. So such set is hyperbolic set. We introduced the concept of hyperbolic set. This concept was introduced by Smale and Donosov in the same time. Okay. Donosov is introduced for geodesic flows and Donosov diffeomorphism, and Smale for Hausshow by Smale. Okay. Definition. Diffeomorphism F is called a diffeomorphism if F satisfies to Smale axioma that is non-wandering set is hyperbolic, set of periodic points is dense in omega F. So it's condition of chaotic dynamics. In some sense, Morse-Smale also satisfies to this condition, but Morse-Smale has finite number hyperbolic points, but its definition may be used for infinite number hyperbolic points. I say emphasize that axioma and that strong condition on transversality are necessary and sufficient condition for the structural stability of diffeomorphism F Mn to Mn. Okay. According to Smale spectral theory, non-wandering set omega F is the union of pair disjoint closed invariant set, each of which contains dense orbits under action of diffeomorphism F. These sets are called basic sets. An invariant set B of diffeomorphism F is called attractor if there is closed neighborhoods of U of a set B such that Fu belongs to interior U, and intersection gives us attractor B. An invariant set is called repeller, is it attractor for F minus 1. Okay. So a non-trivial basic set lambda of a diffeomorphism M2 is said to be widely exposed on the manifolds M2 if for very point Z every simple closed curve formed by arcs CU and CS is not contractible on M2. So here is picture. We have hyperbolic points and Z and Y, we have intersection, and this loop is not homotopic to 0. It's very important to consider example of basic sets for understanding about what I say. So look at this map. X is equal to X plus Y, Y is equal X plus Y. If we consider this map on Euclidean plane, is not interesting because it map has only one fixed point and stable and unstable manifold, so it's saddle. However, if we consider this map modulo 1, when phase space became two-dimensional torus. This example was shown by Tom to Smale, and Smale understood very many years ago in last century that this map on torus has infinite number periodic points. It's possible to check by hands. So it's possible, very easy to check that if we consider point at the torus with rational coordinates, it will be periodic points. Where is this map satisfied to condition of hyperbology, because eventual value, one of them is lambda less than 1, another lambda more than 1. And there exist two invariant variations, stable and unstable. And if we have any fixed point and consider stable and unstable manifolds of this fixed point, these stable manifolds will be transitive on torus, and for unstable the same, and we get infinite number homoclinic points. It's very, very chaotic dynamics. And how proved by Sinai, first it was proved by Arnold and Sinai with mistake, but Anosov corrected this proof and proved this map is structurally stable. So if we have such map, it means it calls Anosov total algebraic diffeomorphism. We can do some surgery operation which suggested Smale, and get new diffeomorphism of torus, which have one source and non-trivial basic set, which is geometrically some lamination, which is locally scalar set multiplied by interval. So look at next picture. So surgery operation, it is that we take some points, periodic fixed points, and change neighborhoods by 3 points. For example, on this picture, source and 2 saddle points. After that surgery operation, we get new diffeomorphism with some attractor, non-trivial attractor, which is lamination, which each it is locally counter set multiplied by interval, and each one-dimensional curve are dense in this non-wandering set. Okay, non-dense set on torus. It's rather non-trivial set. So below is picture on computer. Okay, sorry. Here is sync. It's a fundamental domain of torus, and this interval gluing with this interval. So after some calculation, we get counter set, and white color is basin of source. Okay, unstable manifolds of source. So we get the diffeomorphism. With one-dimensional widely disposed attractor, the local dimension of attractor is equal to dimension of unstable manifolds. Okay. Okay. It's possible to get. So it's. I would like to emphasize that this attractor will be widely disposed attractor, which is not homotopic, loops homotopic to 0, formed by stable and unstable manifolds. Okay, it's possible to get new example on surface negative curvature, and these attractors will be connected geodesic lamination. Definition: homomorphism P M2 to M2 is called pseudo-Anosov, where is exists P invariant transverse foliation FSFU with common set of singularities S, and pair of transverse measures mu S and mu satisfy the following properties. Each singularity in S is of saddle type with at least 3 separatrices, where exists lambda such where we have such estimation. So we have two foliation with such singularities, stable and unstable. If we consider anodes of diffeomorphism, we have two foliation stable and unstable without singularities, but it's not possible to have foliation without singularities on surfaces negative curvature, so we have two foliation, transitive foliation with saddle singularities, okay? Examples of other disposed attractor on M2. In this year, Zhirov and Plikin, my friends, generalized the surgery operation for pseudo-anodes of homeomorphism. So it's possible to do some surgery operation. We take fixed point and change it, for example, 3 points, saddle points, and one source, or 2 points saddle and 1 point. After that, we get some new diffeomorphism with non-trivial attractor, and complement for non-trivial good is finite number of disks bounded from interior by finite number unstable manifolds at some fixed point or periodic points, which called by me and Plikin boundary periodic points. So I would like that at this moment you understand what is mean complicated attractor on surfaces. It's some lamination which is locally counterset an interval, and each unstable lengths are dense in this complicated set, and the complement is finite number disk, okay, on surfaces. Definition: a bunch B of attractor lambda is the union of a maximal number RB of unstable manifolds of as boundary points of the set lambda accessible from some the same for all points x belonging M2 minus lambda. The number RB is said to be the degree of bunch, okay? Definition: attractor lambda of dimorphism F of genus Mo when 0 is called perfect if M2 minus lambda consists of finite number domains, each of which is homomorphic to disk. I would like to emphasize that if we have non-trivial basic set lambda, it means that our diffeomorphism has infinite number periodic points. This diffeomorphism has chaotic dynamics. So now below is now recent result obtained by me with aspirant Kurenkov. And one-dimensional widely disposed attractor lambda of diffeomorphism F is a perfect attractor. It means that the complement consists of finite number disk, if and only if action in fundamental group gamma is hyperbolic automorphism. So we have very beautiful interrelation between dynamics and between topology. We take diffeomorphism axioma on surfaces, and only know what it possessed by some attractor, perfect attractor. In this case, action in fundamental group is hyperbolic. But we remember from my lecture that if automorphism is hyperbolic, it possessed by geodesic laminations. It's possible to construct unique way geodesic lamination on surfaces. It's such geodesic lamination which consists of recurrent transitive geodesics, and each geodesic dense in this lamination. So we claim if lambda doesn't contain bunches of degree 2, because it's possible, its number doesn't denote a topology, it's possible to do. Then there is homomorphism H, M2 to M2, which maps unstable manifolds of lambda to leaps of geodesic lamination omega U. I would like to emphasize, we take Lobachevsky geometry. We know and understand what is mean straight line in geodesic, in Lobachevsky plane. Very surprised results. There exists such geodesics on Lobachevsky plane. It's clear that Lobachevsky did not think about it. If we consider projection of this geodesic to surface, okay, which is orbit space, some properly group, then closure of this geodesic will be lamination, which is homeomorphic to some attractor of dynamic system. So, if we consider diffeomorphism, axioma diffeomorphism on surface, we have get very many attractors, but this set can be described. If we consider attractors which are widely disposed, that is, have no loops homotopic to zero, then each such attractor homeomorphic to some geodesic lamination, which constructed on using by geodesic of Lobachevsky plane. So we have interrelation between dynamics, topology, and Lobachevsky geometry on surfaces. And I can finish classification widely disposed perfect attractors of diffeomorphism. Look, please, below. Lemma. Let F M2 by 2 be diffeomorphism of closed surface of genus G more than equal to. We widely this perfect perfect attractor. Don't afraid this concept. It's such a attractor which complement consists of finite number disk. Okay, nothing more. When there exists pseudonose of homeomorphism, it's classical homeomorphism was constructed by Thurston. Nielsen did not know about homeomorphism. When there exists pseudonose of homeomorphism and continuous map H, homotopic to identity such that the following properties hold. First, diagram commutative. H maps leaves of stable leaves to stable leaves of Fs of pseudonosov. H maps leaves of Wx on leaf of pseudonosov. H is 1-to-1 on lambda minus gamma, where gamma is union of boundary unstable manifolds in the set of unstable manifolds of boundary periodic points. So if we delete this, H is 1-to-1. So we have almost conjugacy our basic set, dynamics on basic set is pseudonosov. It's surprise results indeed. And I finish my lecture by theorem. Let F and Fy be a diffeomorphism of closed surface of genus G more than 1. The widely disposed attractors, lambda and lambda prime. When there exists a homeomorphism phi M2 such that diagram commutative, so F prime and F are conjugated, if and only if there exists homeomorphism pseudonosov homeomorphism, such that this map set B to the set B prime. Set I come back a little bit. B is the B is the set where we have no B is when unfortunately I don't see this definition. Okay. Yes, let B the set of all periodic points Q of a homomorphism P such that the set consists of exactly 2 periodic points. So we have no 1-to-1. This set can be described very easy. So I finish. When there exists a homomorphism phi conjugating F prime and F on lambda, if and only if pseudonosov homomorphism are conjugated by psi, which maps set B to B prime. Thank you.
Okay, thank you so much. It was very interesting. For now, we don't have any questions, but maybe they will appear in discussion section today.
I will be waiting for you. Okay, thank you.
Thank you so much. Dear listeners, now we have a short break for 10 minutes.
Okay, thank you.
Dear participants, we announce the last lecture of our online international workshop and the last lecture in the mini course devoted to reaction diffusion equations in biology and medicine by Professor Vitaly Volper. Please, Professor.
Thank you. So we begin the last lecture of this course of lectures about reaction diffusion equations. In the previous two lectures, we have discussed some questions about existence and stability of solutions. We considered also some applications, but in this last lecture, we will start not from the mathematical questions, but from the applied questions, and we will see how we can use the mathematical results we discussed before. And we will consider two questions. The first one from population dynamics about evolution of biological species. And the second question concerns mathematical immunology about viral infection. In some sense, the second question can also be related to the first one because we can also consider populations of viruses and populations of cells. So we begin with some questions in population dynamics, and I would like to briefly recall the history of the studies, and probably the first mathematical study in population dynamics was done by Leonard Fibonacci in 13th century, and he, counting the rabbits, he suggested these famous Fibonacci sequences. And about 500 years after that, much time earlier, studied this time not rabbits but human population. In fact, he asked the question whether human population could be restored after the deluge more than 2000 years ago, according to the Bible. And like that, he introduced exponential sequences, and he proved that indeed human population by his time could be really restored after the deluge, when only 3 couples remained. About 100 years later, after earlier, Weierholz introduced this another equation, often called now logistic equation, where we have this U population density and the simple equation du dt. If previously for earlier it was equal Ku, but now we multiply it by 1 minus U, meaning that the reproduction of the population is proportional to the population density U and to available resources 1 minus U. So this is important for us for what follows, so I will stop for a moment at this point. So consumption of resources is proportional to the population density. This is why we have here this minus U. So 1, well, sometimes it is called carrying capacity with notation K here, K equals 1, K is in some sense production of resources minus consumption of resources. So here we have 1 minus U available resources. So we have the reproduction of the population is proportional to this product. And the behavioral solution, of course, is different. Instead of the exponential growth as it was before, we have now a bounded solution of this equation. Again, 100 later, Fisher, we discussed it before, Fisher and Kolmogorov, Petrovsky, Piskunov considered the same equation, but they introduced diffusion. And of course, it becomes much more complete and interesting and complex. And we discussed that such equations describe in particular reaction diffusion waves. And so in the previous lectures, we discussed some questions about existence and stability of such solutions. What seems very interesting for me is the evolution of mathematical models. And I show here this, what we discussed right now, starting with this first equation suggested by Euler, then 100 years later, the logistic equation, 100 years later, this reaction diffusion equation. It was the beginning of the 20th century. So what next? How these models will change next? And one of the direction of this evolution of models is to consider now what is called non-local reaction diffusion equations, shown here. So we have here this integral term, and we will discuss the meaning of this term a little bit later. So discussing these questions in population dynamics related to evolution of biological species, we will begin with non-local reaction diffusion equations. So we have this equation where, so you remember the logistic term before, it was u1 minus u. Now we have, instead of u here, this integral. And before u, well, I explained it. So it was consumption of resources proportional to the population density. So in classical population dynamics, it is assumed that individuals consume resources exactly at the same space point x where they are located. This is why here we have had 1 minus u of x and of t. Now we suppose that these resources are consumed not only at this particular space point, but in some area around this point. In this schematic figure here below, I show it in this way. So we have some individual, it is located, its average location is here at this point, but the resources are consumed in some area around it. But then if we take another individual who is located here, so this area of consumption of resources is here, so these two areas can overlap. And this is very important because this model in this case shows, it can describe the intraspecific competition of individuals. So this is very important. From the mathematical point of view, now because of this non-local consumption of resources, we have this integral. This integral shows how the consumption of resources depends on distance. If our individual is located at the point x, so it consumes resources at all points y around this point x, and this is different kernel. The difference kernel shows how this consumption of resources depends on the distance. So this is what we call non-local reaction diffusion equation, and we will discuss a little bit the properties of its solutions. Again, this equation, so it can be easily verified as before when we had 1 minus u here in the brackets, then of course u equal 1 is a constant stationary solution of this equation. We discussed it before. Now we suppose if the integral of phi equals 1, so u equal 1 is also a constant stationary solution of this equation. It can be easily verified. We substitute here, instead of u, we substitute 1. The integral of phi equals 1. So this is 0, everything is 0. It's a stationary solution. So it is a constant stationary solution of this equation. And we discussed in the previous lecture that we can easily study stability of this constant stationary solution. So what we do, we consider the linearized operator the corresponding eigenvalue problem, which can also contains now this integral. And then a very simple, well, we can even analytically study this simple eigenvalue problem. For example, we can simply apply the Fourier transform to this equation, and we obtain the explicit expression for the eigenvalues. And it appears, and this is very interesting, that such a simple mathematical analysis can give non-trivial results. It appears that this lambda can become positive because this sinus changes sign, and the sinus, well, because I consider a particular kernel shown here, so I do explicit calculations. So we have this Fourier transform, we have the sinus, it changes sign, so lambda, the eigenvalue, can become positive. This means that our constant solution u equals 1 can lose its stability. We discussed stability equations yesterday. So positive eigenvalues, the solution can lose its stability. And this is the principal difference between the local problem when we have here 1 minus u, when this solution u equal 1 is always stable, and the non-local problem where this solution can lose its stability. So from the mathematical point of view, here we see this difference between the two problems. And then this is numerical simulation, shows what happens with this solution u equal 1. So this is our stationary solution, u equal 1. This is, maybe you see here, there is a small perturbation of this solution. And as we discussed, the stability and instability yesterday, so we take a small perturbation, and since this solution is not stable, the perturbation begins to grow. You see here kind of oscillation, space oscillations appear. These space oscillations become larger and larger in time, and this solution converges to another stationary solution shown here. It's a stationary solution which is periodic in space. So our solution u equal 1 is unstable, can be unstable, it depends on parameters, can be unstable, and in this case there's a bifurcation of this periodic in space solution. So the next step of our analysis, you see here we use this previous theories, stability in particular. We continue with our analysis. So now reaction diffusion waves, also we discussed in the previous two lectures. So before these waves, we had a propagation of this wave with a constant speed and a constant profile. It was a constant here. So now here it's not a constant, but it is a periodic in space function, because this solution u equal 1 is unstable. There is this periodic solution appears, and it propagates like that. So instead of usual waves, which we discussed before, we have what is called periodic waves. Here we see the same wave for some fixed moment of time. So we have this x variable, u of x for some fixed value of t. We can represent the same solution in a different form. We have, as before here, this x variable, but here we take time, and these lines, they show the level lines of this solution. What this means? This means that here, you remember, for this propagation, so propagation, we start in the center of the interval, and it becomes larger and larger. So it's exactly what we see here for the level lines of this solution. We start from the center of the interval. The solution propagates to the right, to the left, and these space oscillations here, it's since these are level lines, so these space oscillations here are represented here like these lines. So this is the same solution represented as level lines on the X and T plane. I have spent several minutes to explain this because, of course, it's very simple, but we will need it before, so please keep in mind this representation of solution on this X and T plane. So the next step in our construction is pulses. So we discussed also pulses in the previous two lectures. We proved the existence of pulses, and we even proved that pulses are unstable yesterday. But this instability was proved for the local equation. So what happens for the non-local equation? And in the first lecture, maybe some of you know, we discussed the question about the existence of pulses for this non-local equation. And I indicated that instead of a single pulse as before for the local equation, here we have two pulses. One of them is unstable, the same as for the local equation, but another one becomes stable. And this is again a very important difference in these two equations. So now we have existence and stability of these pulses. So a solution like that. And moreover, if we change the initial condition for this equation, we can also obtain not a single pulse like that, but several pulses and many pulses, as many as we like. It depends on the initial conditions. And if you have several pulses like that shown here, these red lines, it's for a fixed moment of time, it's X, it's for a fixed moment of time, you have the several pulses. But then if we observe what happens with these pulses in time, it appears that they are not stationary. This is not a stationary solution. These pulses slowly move from each other, shown as these green lines. So these green lines, they show the maxima of this solution. For example, here we have 5 pulses, 5 maxima. So we have these 5 green lines, and you see these green lines, they are not exactly vertical, but they go here a little bit to the left, a little bit to the right in time. For pulses, this is T, also time. So these pulses move slowly one from another. So to summarize what happens with these non-local equations, we have that here we have some new solutions in comparison with the local equation. These are periodic waves, stable pulses, and multiple pulses. And now we will apply this, what we learned about non-local equation to describe evolution of biological species. And here I refer to Darwin's book on the origin of species. It is considered as the most influential scientific book of all times. It's a big book published in 1859, by the way, much after when Darwin developed his theory. He was waiting for a long time. He was not sure about publication of this book. And in this big book, there is only one figure, and this figure is shown here. This is a famous Darwin's diagram where he summarizes his theory of evolution of biological species as a result of natural selection. And each line in this diagram corresponds to one biological species. This horizontal axis, for him, he explained in his book, it corresponds to how much these species differ from each other. In our modern terminology, we can say that this is phenotype. So the difference between biological species. And this vertical variable is time. So let us keep it in mind. So our purpose now is to explain this diagram from the mathematical point of view. that, we need to introduce this space variable x, which corresponds now not to the real physical space, but to phenotype. So Darwin's definition of biological species, it is a group of individuals with a similar phenotype. So what means phenotype? Phenotype is some characterization of these animals. It can be, for example, their size, their form, or some other characterization. In this schematic figure, I showed these different animals, different species. For example, if we measure their size, so now then our variable x is the size of these animals. There are small animals, there are big animals, and this is our variable x. Another important point which we need below a little bit later is that if we consider some biological species, for example, elephants, well, they are all similar to each other, but they are not identical to each other. Some of them are a little bit bigger, some of them are a little bit smaller. So if we construct the density distribution of these animals with respect to their size, it will be such kind of a distribution. So there is some average value here and some distribution, sufficiently narrow distribution around this average value. So for us, in our mathematical description, biological species is such distribution. It looks like a pulse, such pulse distribution in the space of phenotypes. X is our phenotype variable, u of x is this distribution, and such distribution characterizes biological species. So if we have several such distributions separated from each other, then we have several different biological species. So this is our mathematical interpretation of biological species in Darwin's definition. So what we have here, so now it is almost done. We have this solution, for example, this pulse solution shown here, phenotype variable x, the solution u of x, it's this density distribution. So how we relate this solution to this diagram? So each line here, according to Darwin, corresponds to one biological species. In our definition, it's a distribution like that. But this is a very narrow distribution around some average value. So this average value, the position of this maximum, corresponds to this position of this point here. So we have this x variable here, x variable here. We take this maximum, it is located here. This corresponds to our biological species. But then Darwin considers it on the xt plane. So we will also consider our solutions on the xt plane. For example, if we consider this pulse solution, pulse is a stationary solution. It does not depend on time. So the position of this maximum does not change in time. So on this x and t plane, we will obtain this vertical line. So we have this one biological species corresponding to this pulse solution here, another one here, another one here. But the purpose of this diagram was to illustrate his whole theory. So there are many other patterns shown in this diagram, and with this modeling we did before, we can explain now all these patterns shown in this diagram. For example, you see here the several lines, several pulses. They are not vertical. In fact, the distance between them increases slowly in time here, and this corresponds to the solution with multiple pulses. Of course, what is very important and very often discussed in mathematical biology, mathematical ecology, is the emergence of biological species, how the species emerge. And here he shows in many times how if you take a point here, you see there are several lines emerge from this point. So there are several species appear from this point. And this corresponds to our description here. I brought your attention to this periodic traveling waves, this representation on the XT plane, level lines of solutions. So if we start from this point, we had here only one species, but with time, this species divides into two, then again into two more, and so far new and new species appear. So this is how the species appear, and this emergence of new species correspond to all these points here. Of course, there are many other interesting things. For example, we see several of them start here, but all of them disappear, and only two of them survive. Well, he explains that only the most fitted survive, and rather often these most fitted are from the side the most left and the most right, and so on. And we also, I don't present it here, but we can also obtain it in simulations. Another important point here is extinction of species. You see, for example, this line goes like that, and then it disappears. Why it disappears? Because it begins to compute with this one, and because of this competition between different species, some of them can disappear. So we can describe all these patterns with the help of non-local reaction diffusion equations and systems of equations. So summarizing this part of this lecture, we can say that evolution of biological species in the space of phenotypes, according to Darwin's definition, can be described by non-local reaction diffusion equations, and density distributions are mainly characterized by single and multiple pulses and periodic waves. Of course, what I show you here, it's a just brief description. There are many other interesting questions, and among them, I will present two of them, but we will not discuss it now. So Darwin's definition of species is not the only one. Rather often now another definition of species is used, given by Mayer, that biological species is a group of individuals that can reproduce among themselves. So an interesting question is how Darwin's definition of species is related to Mayer's definition of species. And another question which seems to me very interesting, though maybe a little bit philosophical, in fact, why we have this species at all. This question can also be answered, maybe at least in the framework of modeling we discussed before. So, and the second part of this lecture is the applications of these mathematical theories to mathematical immunology, and namely to viral infections. And as I mentioned before, in some sense, it can also be considered as related to population dynamics. So we have viruses, we have cells, kind of populations. And an interesting, of course, question for us, we have two teams, a team of viruses, a team of cells. The battlefield is our body. So who will win in this battle? So this is, of course, important. And I will, to introduce some mathematical models, I will briefly, very schematically recall what happens when this battle starts. We have viruses which penetrate the body. Viruses cannot reproduce themselves. They enter cells, host cells. They reproduce inside these host cells. Then they go outside. the cell can survive or it can die after some time. So viruses not only reproduce, but they also damage cells. And of course, our body tries to eliminate this infection with the immune response. It's a very, very complex system with many cells involved in that, in particular antigen-presented cells, which activate B and T lymphocytes. T lymphocytes, cytotoxic T lymphocytes kill infected cells. B lymphocytes produce antibodies which eliminate free virions. So it's of course very schematically, very simplified what happens during the immune response to viral infections. And now with this very simplified representation, we can suggest a simple mathematical model. It is simple but not trivial in the sense that it describes some of these phenomena happening during viral infection. And in fact, it's two ordinary differential equations for the concentration of virus, for the concentration of immune cells. In the concentration of virus, we have this logistic reproduction term, the same as we discussed before for these population dynamics problems. And we have the elimination of virus by immune cell C. And the second equation is the equation for the immune cells. So again, we have this logistic equation for immune cells. But what is important here is that for the adaptive immune response, it is called clonal expansion of immune cells depends on the concentration of virus. So it's virus itself which initiates production of the cells. This is why there is a function which depends on the concentration of virus. But virus can also kill cells. This is why this death of the cells can also depend on the concentration of virus. Here, this tau and mu, they correspond to to time delay, because this immune response, clonal expansion of immune cells, and also cell death can happen with some time delay. So I will say a couple of words a little bit later. But if we forget for a moment about time delay, we have two ordinary differential equations, and we can easily study its behavior as usual, stationary points, trajectories, all that. Of course, I will not stop on this in detail, but just to mention that so there are several, for example, here in this figure, there are several stationary points. For example, this one, V equals 0 corresponds to complete virus elimination. Here, V equals 0, but V equal 1, but C equals 0. It corresponds to exhaustion of immune cells, which is also, of course, known in immunology. There are some other stationary points. We will not discuss everything, but what is important here, that depending on the initial condition, biologically speaking, depending on the initial viral load, if the initial viral load is small, V is small, this trajectory goes this way, or here in this figure, this trajectory goes this way. So if the initial viral load is small, so virus is completely eliminated, and here afterwards we have even remaining immune cells called memory cells. But if here the initial viral load is large, the initial condition is here, this trajectory goes this way, and in this case we have chronic disease, exhaustion of immune cells, and all these bad consequences of viral infection. So we see here that behavior of solutions depends on the initial viral load, but also, and I don't discuss it here, on the strength of immune response, which is very important for all these considerations. So about time delay, you see here there are two time delays. Since the problems with time delay were largely discussed during this workshop, so I do this short remark here that in fact we can also have here state-dependent delay, because duration of cell cycle and clonal expansion and duration of cell apoptosis can depend on virus concentration, and this was mentioned during lectures and during discussions. But I will not discuss it today. And we need to continue with this construction of our models. We can study these two equations, but to make it simpler now, I will reduce this model of these two equations to the single equation, and I will show what will happen, how we can do it. Let us assume that there are large constants here, then we can use what is called quasi-stationary approximation. So we say that this derivative is 0, we have an algebraic equation, we express this from this, so this expression equals 0, we express C from here, we obtain C as a function of V virus, we substitute the C in this first equation, and we obtain only one equation for virus concentration, and this equation has exactly this form. Quite simple equation, one differential equation, possibly with time delay. So we can study, of course, without time delay, it is quite trivial. With time delay, it becomes a little bit less trivial. So we can study, well, there are stationary points. We can study the stability, their stability by linear stability analysis. And it appears that these points can be stable or they can be unstable with time oscillations because of time delay. What is also interesting that under some conditions, it is possible to prove global stability. This is already a little bit more sophisticated mathematically. But another interesting question, what happens if this local or global stability doesn't hold? And here, it is a very simple equation, one differential equation with time delay. But it appears that even for such a simple equation, behavioral solutions can be quite complex, and we can have not only periodic time oscillations, but also period doubling bifurcations, transition to chaos, and all this post-chaotic behavior, Sharkovsky sequences, and all this interesting nonlinear dynamics. So the next step in our construction, we introduce diffusion. So our previous equation was this one. So this, I recall that this term, logistic term, corresponds to virus replication. This last term corresponds to virus elimination by immune response, with this function, which this immune response and this quasi-stationary approximation is depends on virus concentration, possibly with time delay because of clonal expansion of immune cells. So we have a reaction diffusion equation with time delay. In the first lecture, we discussed the question about wave existence for the scalar reaction diffusion equation. So it was exactly this equation, but without time delay. It appears that time delay makes here a lot of difference. If we don't have time delay, we have simple reaction diffusion equations, and I showed you, it was just one slide to prove the existence of waves. In this case, it was very simple, almost trivial. With a small difference here, we introduce this time delay. It appears the problem becomes very, very complex. And it depends also on the form of the function f. And it appears that it's very sophisticated mathematical methods are necessary to study the existence of solutions, at least in some cases. Not always it can be done, but we will not discuss it now anymore. And we continue now with numerical simulations, and the main results of these simulations are shown schematically here. Also, I mentioned in my previous lectures that it is possible that we have only one wave, like this one, or like this one, or we can have two different waves propagating with different speeds, like this one. So this wave propagates with the speed c0, this wave propagates with the speed c1. If c0 is larger than c1, so we have this like two steps like that. And this is exactly what we observe here for this problem. And from the point of view of mathematical immunology, this result means that we have three different regimes of infection spreading in the body, in the tissue. The first one is this green line shown here. So we have this infection, virus concentration propagates like that. And afterwards, we have a low level of infection. So the first regime corresponds to low dose infection. The second regime corresponds to this dotted red line shown here. Right away, we arrive here to the high level of infection. And the third regime, when we have two consecutive transitions, first the transition to low level infection, and after some time to high level infection. And I showed before this example, so it's in fact the problem here is a little bit more difficult, but it illustrates well what we here. By the way, it is for two-dimensional model of immune response, so it's corresponds to what we discussed now. So we have this first wave of infection propagating here, and then the second wave of infection propagating here. Then if we introduce time delay in this equation, and I also mentioned it before, then this solution can become unstable, and we have this time oscillations, time-space oscillations here between these two infection waves. And last several minutes, I will briefly discuss the question about virus mutations, evolution, and resistance to treatment. It's also related to the first part of this lecture, to the evolution of biological species. Of course, virus is not biological species, but it is called sometimes quasi-species. And from the mathematical point of view, there are many things in common with what we discussed before, evolution of biological species. Here, equations are different, the results are also different, but the main idea, also, we don't have time to discuss in detail, but the main idea is that, yes, a virus, of course, can mutate and can evolve because of these mutations. Now, previously, we considered the space of phenotypes. Now we consider the space of genotypes. We consider viral quasi-species as density distributions in the space of genotypes. And you see that it can change. It can go here, this X, this is T. So this distribution goes from here to here. So virus evolves. Here you see that instead of this one virus, viral quasi-species, it can split also on several quasi-species and so on. Behavior can be quite complex, especially if we introduce time delay. And this last figure here shows how this viral quasi-species can react on antiviral treatment. So here, this X variable, this is genotype. So this is T variable for T. In the beginning, for small t, we have this virus, which is shown here. Then we apply treatment, antiviral treatment at this moment of time. So we kill this virus. But instead of this virus, we obtain another virus, which is worse than the previous one because our antiviral treatment acted on this one, but not on this one. So instead of this previous virus, we obtain a new virus resistant to treatment, and it appears exactly because of treatment. So unfortunately, we don't have more time to discuss these very interesting and important questions. So some concluding remarks are already to all three lectures. So what we discussed during these 3 days is that reaction diffusion equations arise in various applications. We discussed existence and stability of solutions, in particular existence and stability of waves, pulses, and constant solutions. We discussed a little bit non-local and delay reaction diffusion equations, and we applied this mathematical theory to study some questions in population dynamics and mathematical immunology. So this is the end of this third and last lecture. And to finish my lectures, but also this is the last lecture of this workshop. So I would like to thank the organizers for this very nice conference, very nice and precise organization. Also to thank all participants and listeners, and to wish everyone stay healthy, even if we have some problems with this epidemic. Thank you very much.
All right, thank you, Professor. And you will have more time to express your feelings during the discussion session. Thank you for your lecture. And now we have some questions for you. So the first question consists of several questions. I will read all of them now, one by one. About the system of the waves, can we describe them as the simple waves W of x minus ct? Can they be treated mathematically or just explorated by simulations? Is it due to delay? Why? Thank you.
Okay, difficult to answer several questions at the same time, but I will try.
Thank you.
So no, the system of waves, this is not a single wave, and it cannot be described as Wx minus Ct. This is the first question. The second question, we can study such objects mathematically, so it's not Wx minus Ct, but still we can study them mathematically, their existence, their stability, and also in numerical simulations. And the existence and behavior, I would say the existence and stability convergence of such solutions are not related to time delay. So they exist in the equation without time delay. Then, of course, we can also introduce time delay, and time delay can influence the behavior of such solutions, but such solutions exist even without time delay.
All right, thank you. The next question is, you have shown the fruitfulness of the non-local generalization of the second factor of the right-hand side, u multiplied by 1 minus u. Do you expect anything from such a generalization of its first factor?
Unfortunately, the sound was not very clear, so I am not sure that I understand the question. So I understand that the question about 1 minus u in the right-hand side, right? And what else?
Okay, do you expect anything from such a generalization of its first factor?
Generalization. So if we multiply the equation by 1 minus u, this is the question?
Yes, I suppose so. Maybe you can try to look at the question on the
okay.
question and answers.
Okay, so maybe I can see the... Yeah, why not? Okay. Yeah, I see the question. Yeah, you have shown the... Okay, I see. So, of course, what I showed here, it was just several examples. There are many other non-local equations. And also the first term, so in this product u1 minus u, it can be also the non-local term in the place of u. So indeed, there are different equations and the results can be different indeed, yes. But I cannot answer in more detail now, it would take more time.
All right, thank you. The next question is, interesting, thank you, Professor. When it comes to modeling natural phenomena, what are the main limits of the non-local and local reaction diffusion models?
The main limits of the, well, so when we study some processes, biological, biomedical, or whatever, of course, we need to choose our model which is appropriate to describe this process. So it can be local or non-local, depending on the processes which we describe. So I cannot answer this question in general. We need to consider each particular application, and we need to decide according to these applications whether we can use local or non-local models.
All right, thank you very much, Professor. We are done with the questions, and all we can do now is thank you for the great course of lectures you gave us. It's been a great pleasure listening to you.
Thank you.
Yes, now I would like to remind the audience that all the recordings are available. You can find them using the same Microsoft Teams links or on YouTube on the RUDN University channel. You can find the links on our website. And now in 8 minutes, the discussion session starts. It will be united with the closing ceremony. You can join the discussions using the link that has just been posted in the question and answers, or you can find the link in the program. Thank you very much. Please don't stay on this broadcast. Yes, use the link. Thank you.
У нас в течение 5 минут, я так понял, да?
I
Okay. Very good, actually. Okay, I took a glass of vodka.